Section 2 of The Advance of Science in the Last Half-Century by T.H. Huxley. The development of every branch of physical knowledge presents three stages which, in their logical relation, are successive. The first is the determination of the sensible character and order of the phenomena. This is natural history, in the original sense of the term, and here nothing but observation and experiment avail us. The second is the determination of the constant relations of the phenomena thus defined, and their expressions in rules or laws. The third is the explication of these particular laws by deduction from the most general laws of matter and motion. The last two stages constitute natural philosophy in its original sense. In this region, the invention of verifiable hypotheses is not only permissible, but is one of the conditions of progress. Historically, no branch of science has followed this order of growth, but, from the dawn of exact knowledge to the present day, observation, experiment, and speculation have gone hand in hand, and whenever science has halted or strayed from the right path, it has been either because its votaries have been content with the mere unverified or unverifiable speculation, and this is the commonest case, because observation and experiment are hard work, while speculation is amusing, or it has been because the accumulation of details of observation has for a time excluded speculation. The progress of physical science since the revival of learning is largely due to the fact that men have gradually learned to lay aside the consideration of unverifiable hypotheses, to guide observation and experiment by verifiable hypotheses, and to consider the latter not as ideal truths, the real entities of an intelligible world behind phenomena, but as a symbolic language by the aid of which nature can be interpreted in terms apprehensible by our intellects. And if physical science, during the last 50 years, has attained dimensions beyond all former precedent, and can exhibit achievements of greater importance than any former such period can show, it is because able men, animated by the true scientific spirit, carefully trained in the method of science, and having at their disposal immensely improved appliances, have devoted themselves to the enlargement of the boundaries of natural knowledge in greater number than during any previous half-century of the world's history. I have said that our epoch can produce achievements in physical science of greater moment than any other has to show, advisedly, and I think that there are three great products of our time which justify the assertion. One of these is that doctrine concerning the constitution of matter which, for want of a better name, I will call molecular. The second is the doctrine of conservation of energy. The third is the doctrine of evolution. Each of these was foreshadowed, more or less distinctly, in former periods of the history of science, and so far is either from being the outcome of purely inductive reasoning, that it would be hard to overrate the influence of metaphysical and even of theological considerations upon the development of all three. The peculiar merit of our epoch is that it has shown how these hypotheses connect a vast number of seemingly independent partial generalizations, that it has given them that precision of expression which is necessary for their exact verification, and that it has practically proved their value as guides to the discovery of new truth. All three doctrines are intimately connected, and each is applicable to the whole physical cosmos. But as might have been expected from the nature of the case, the first two grew, mainly, out of the consideration of physico-chemical phenomena, while the third, in great measure, owes its rehabilitation, if not its origin, to the study of biological phenomena. In the early decades of this century, a number of important truths applicable in part to matter in general, and in part to particular forms of matter, had been ascertained by the physicists and chemists. The laws of motion of visible and tangible, or molar, matter had been worked out to a great degree of refinement, and embodied in the branches of science known as mechanics, hydrostatics, and pneumatics. These laws had been shown to hold good, so far as they could be checked by observation and experiment, throughout the universe, on the assumption that all such masses of matter possessed inertia, and were susceptible of acquiring motion in two ways, firstly by impact, or impulse from without, and secondly by the operation of certain hypothetical causes of motion termed forces, which were usually supposed to be resident in the particles of the masses themselves, and to operate at a distance, in such a way as to tend to draw any two such masses together, or to separate them more widely. With respect to the ultimate constitution of these masses, the same two antagonistic opinions which had existed since the time of Democritus and of Aristotle were still face to face. According to one, matter was discontinuous and consisted of minute indivisible particles or atoms, separated by a universal vacuum. According to the other, it was continuous, and the finest distinguishable or imaginable particles were scattered through the attenuated general substance of the plenum. A rough analogy to the latter case would be afforded by granules of ice diffused through water; to the former, such granules diffused through absolutely empty space. In the latter part of the 18th century, the chemists had arrived at several very important generalizations respecting those properties of matter with which they were especially concerned. However plainly ponderable matter seemed to be originated and destroyed in their operations, they proved that, as mass or body, it remained indestructible and ingenerable, and that, so far, it varied only in its perceptibility by our senses. The course of investigation further proved that a certain number of the chemically separable kinds of matter were unalterable by any known means, except in so far as they might be made to change their state from solid to fluid, or vice versa, unless they were brought into contact with other kinds of matter, and that the properties of these several kinds of matter were always the same, whatever their origin. All other bodies were found to consist of two or more of these, which thus took the place of the four elements of the ancient philosophers. Further, it was proved that, in forming chemical compounds, bodies always unite in a definite proportion by weight, or in simple multiples of that proportion, and that, if any one body were taken as a standard, every other could have a number assigned to it as its proportional combining weight. It was on this foundation of fact that Dalton based his re-establishment of the old atomic hypothesis on a new empirical foundation. It is obvious that if elementary matter consists of indestructible and indivisible particles, each of which constantly preserves the same weight relatively to all the others, compounds formed by the aggregation of 2, 3, 4, or more such particles must exemplify the rule of combination in definite proportions deduced from observation. In the meanwhile, the gradual reception of the undulatory theory of light necessitated the assumption of the existence of an ether filling all space. But whether this ether was to be regarded as a strictly material and continuous substance was an undecided point, and hence the revived atomism escaped strangling in its birth. For it is clear that if the ether is admitted to be a continuous material substance, Democritic atomism is at an end and Cartesian continuity takes its place. The real value of the new atomic hypothesis, however, did not lie in the 2 points which Democritus and his followers would have considered essential, namely, the indivisibility of the atoms and the presence of an interatomic vacuum, but in the assumption that, to the extent to which our means of analysis take us, material bodies consist of definite minute masses, each of which, so far as physical and chemical processes of division go, may be regarded as a unit, having a practically permanent individuality. Just as a man is the unit of sociology, without reference to the actual fact of his divisibility, so such a minute mass is the unit of physico-chemical science, that smallest material particle which under any given circumstances acts as a whole. Molecule would be the more appropriate name for such a particle. Unfortunately, chemists employ this term in a special sense, as a name for an aggregation of their smallest particles, for which they retain the designation of atoms. The doctrine of specific heat originated in the 18th century. It means that the same mass of a body, under the same circumstances, always requires the same quantity of heat to raise it to a given temperature, but that equal masses of different bodies require different quantities. Ultimately, it was found that the quantities of heat required to raise equal masses of the more perfect gases through equal ranges of temperature were inversely proportional to their combining weights. Thus, a definite relation was established between the hypothetical units and heat. The phenomena of electrolytic decomposition showed that there was a like close relation between these units and electricity. The quantity of electricity generated by the combination of any two units is sufficient to separate any other two which are susceptible of such decomposition. The phenomena of isomorphism showed a relation between the units and crystalline forms. Certain units are thus able to replace others in a crystalline body without altering its form, and others are not. Again, the laws of the effect of pressure and heat on gaseous bodies, the fact that they combine in definite proportions by volume, and that such proportion bears a simple relation to their combining weights, all harmonized with the Daltonian hypothesis, and led to the bold speculation known as the law of Avogadro, that all gaseous bodies under the same physical conditions contain the same number of units. In the form in which it was first enunciated, this hypothesis was incorrect. Perhaps it is not exactly true in any form, but it is hardly too much to say that chemistry and molecular physics would never have advanced to their present condition unless it had been assumed to be true. Another immense service rendered by Dalton, as a corollary of the new atomic doctrine, was the creation of a system of symbolic notation, which not only made the nature of chemical compounds and processes easily intelligible and easy of recollection, but, by its very form, suggested new lines of inquiry. The atomic notation was as serviceable to chemistry as the binomial nomenclature and the classificatory schematism of Linnaeus were to zoology and botany. Side by side with these advances arose in another, which also has a close parallel in the history of biological science. If the unit of a compound is made up by the aggregation of elementary units, the notion that these must have some sort of definite arrangement inevitably suggests itself, and such phenomena as double decomposition pointed, not only to the existence of a molecular architecture, but to the possibility of modifying a molecular fabric without destroying it, by taking out some of the component units and replacing them by others. The class of neutral salts, for example, includes a great number of bodies in many ways similar, in which the basic molecules, or the acid molecules, may be replaced by other basic and other acid molecules without altering the neutrality of the salt. Just as a cube of bricks remains a cube so long as any brick that is taken out is replaced by another of the same shape and dimensions, whatever its weight or other properties may be. Facts of this kind give rise to the conception of types of molecular structure, just as the recognition of the unity in diversity of the structure of the species of plants and animals gave rise to the notion of biological types. The notation of chemistry enabled these ideas to be represented with precision, and they acquired an immense importance when the improvement of methods of analysis, which took place about the beginning of our period, enabled the composition of the so-called organic bodies to be determined with rapidity and precision. At present, more organic analyses are made in a single day than were accomplished before Liebig's time in a whole year. A large proportion of these compounds contain not more than 3 or 4 elements, of which carbon is the chief, but their number is very great, and the diversity of their physical and chemical properties is astonishing. The ascertainment of the proportion of each element in these compounds affords little or no help towards accounting for their diversities, widely different bodies being often very similar or even identical in that respect. And, in the last case, that of isomeric compounds, the appeal to diversity of arrangement of the identical component units was the only obvious way out of the difficulty. Here again, hypothesis proved to be of great value. Not only was the search for evidence of diversity of molecular structure successful, but the study of the process of taking to pieces led to the discovery of the way to put together, and vast numbers of compounds, some of them previously known only as products of the living economy, have thus been artificially constructed. Chemical work at the present day is to a large extent synthetic or creative, that is to say, the chemist determines theoretically that certain non-existent compounds ought to be producible, and he proceeds to produce them. It is largely because the chemical theory and practice of our epoch have passed into this deductive and synthetic stage that they are entitled to the name of the new chemistry which they commonly receive. But this new chemistry has grown up by the help of hypotheses, such as those of Dalton and of Avogadro, and that the singular conception of bonds invented to colligate the facts of valency or atomicity, the first of which took some time to make its way, while the second fell into oblivion, for many years after it was propounded, for lack of empirical justification. As for the third, it may be doubted if anyone regards it as more than a temporary contrivance. But some of these hypotheses have done yet further service. Combining them with the mechanical theory of heat and the doctrine of the conservation of energy, which are also products of our time, physicists have arrived at an entirely new conception of the nature of gaseous bodies and of the relation of the physico-chemical units of matter to the different forms of energy. The conduct of gases under varying pressure and temperature, their diffusibility, their relation to radiant heat and to light, the evolution of heat when bodies combine, the absorption of heat when they are dissociated, and a host of other molecular phenomena, have been shown to be deducible from the dynamical and statical principles which apply to molar motion and rest, and the tendency of physico-chemical science is clearly towards the reduction of the problems of the world of the infinitely little, as it already has reduced those of the infinitely great world to questions of mechanics. In the meantime, the primitive atomic theory, which has served as the scaffolding for the edifice of modern physics and chemistry, has been quietly dismissed. I cannot discover that any contemporary physicist or chemist believes in the real indivisibility of atoms, or in an interatomic matterless vacuum. Atoms appear to be used as mere names for physico-chemical units which have not yet been subdivided, and molecules for physico-chemical units which are aggregates of the former. And these individualized particles are supposed to move in an endless ocean of a vastly more subtle matter, the ether. If this ether is a continuous substance, therefore, we have got back from the hypothesis of Dalton to that of Descartes. But there is much reason to believe that science is going to make a still further journey, and in form, if not altogether in substance, to return to the point of view of Aristotle. The greater number of the so-called elementary bodies now known had been discovered before the commencement of our epoch, and it had become apparent that they were by no means equally similar or dissimilar, but that some of them, at any rate, constituted groups, the several members of which were as much like one another as they were unlike the rest. Chlorine, iodine, bromine, and fluorine thus formed a very distinct group, sulfur and selenium another, boron and silicon another, potassium, sodium, and lithium another, and so on. In some cases, the atomic weights of such allied bodies were nearly the same, or could be arranged in series, with like differences between the several terms. In fact, the elements afforded indications that they were susceptible of a classification in natural groups, such as those into which animals and plants fall. Recently this subject has been taken up afresh, with a result which may be stated roughly in the following terms. If the 65 or 68 recognized elements are arranged in the order of their atomic weights, from hydrogen, the lightest, as unity, to uranium, the heaviest, as 240, the series does not exhibit one continuous progressive modification in the physical and chemical characters of its several terms, but breaks up into a number of sections, in each of which the several terms present analogies with the corresponding terms of the other series. Thus the whole series does not run A, B, D, E, F, G, H, I, K, etc., but A, B, C, D, capital A, capital B, capital C, capital D, alpha, beta, gamma, delta, etc., so that it is said to express a periodic law of recurrent similarities. Or the relation may be expressed in another way. In each section of the series, the atomic weight is greater than in the preceding section, so that if W is the atomic weight of any element in the first segment, W plus X will represent the atomic weight of any element in the next, and W plus X plus Y the atomic weight of any element in the next, and so on. Therefore, the sections may be represented as parallel series, the corresponding terms of which have analogous properties, each successive series starting with a body the atomic weight of which is greater than that of any in the preceding series, in the following fashion. Column 1, D, C, B, A, W. Column 2, capital D, capital C, capital B, capital A, W plus X. Column 3, delta, gamma, beta, alpha, W plus X plus Y. This is a conception with which biologists are very familiar, animal and plant groups constantly appearing as series of parallel modifications of similar and yet different primary forms. In the living world, facts of this kind are now understood to mean evolution from a common prototype. It is difficult to imagine that in the not living world they are devoid of significance. Is it not possible, nay probable, that they may mean the evolution of our elements from a primary undifferentiated form of matter? 50 years ago such a suggestion would have been scouted as a revival of the dreams of the alchemists. At present it may be said to be the burning question of physico-chemical science. In fact, the so-called vortex ring hypothesis is a very serious and remarkable attempt to deal with material units from a point of view which is consistent with the doctrine of evolution. It supposes the ether to be a uniform substance, and that the elementary units are, broadly speaking, permanent whirlpools or vortices of this ether, the properties of which depend on their actual and potential modes of motion. It is curious and highly interesting to remark that this hypothesis reminds us not only of the speculations of Descartes, but of those of Aristotle. The resemblance of the vortex rings to the tourbillons of Descartes is little more than nominal, but the correspondence between the modern and the ancient notion of a distinction between primary and derivative matter is, to a certain extent, real. For this ethereal earth stuff of the modern corresponds very closely with the protyle of Aristotle, and the materia prima of his medieval followers, while matter, differentiated into our elements, is the equivalent of the first stage of progress towards the hecatile, or finished matter, of the ancient philosophy. If the material units of the existing order of nature are specialized portions of a relatively homogeneous materia prima, which were originated under conditions that have long ceased to exist, and which remained unchanged and unchangeable under all conditions, whether natural or artificial, hitherto known to us, it follows that the speculation that they may be indefinitely altered, or that new units may be generated under conditions yet to be discovered, is perfectly legitimate. Theoretically, at any rate, the transmutability of the elements is a verifiable scientific hypothesis, and such inquiries as those which have been set afoot into the possible dissociative action of the great heat of the sun upon our elements are not only legitimate, but are likely to yield results which, whether affirmative or negative, will be of great importance. The idea that atoms are absolutely ingenerable and immutable manufactured articles stands on the same sort of foundation as the idea that biological species are manufactured articles stood 30 years ago, and the supposed constancy of the elementary atoms during the enormous lapse of time measured by the existence of our universe is of no more weight against the possibility of change in them in the infinity of antecedent time than the constancy of species in Egypt since the days of Ramses or Cheops is evidence of their immutability during all past epochs of the earth's history. It seems safe to prophesy that the hypothesis of the evolution of the elements from a primitive matter will, in future, play no less a part in the history of science than the atomic hypothesis which, to begin with, had no greater, if so great, an empirical foundation. It may perhaps occur to the reader that the boasted progress of physical science does not come to much, if our present conceptions of the fundamental nature of matter are expressible in terms employed more than 2000 years ago by the old master of those that know. Such a criticism, however, would involve forgetfulness of the fact that the connotation of these terms in the mind of the modern is almost infinitely different from that which they possessed in the mind of the ancient philosopher. In antiquity they meant little more than vague speculation. At the present day they indicate definite physical conceptions, susceptible of mathematical treatment and giving rise to innumerable deductions, the value of which can be experimentally tested. The old notions produced little more than floods of dialectics. The new are powerful aids towards the increase of solid knowledge. Everyday observation shows that, of the bodies which compose the material world, some are in motion and some are, or appear to be, at rest. Of the bodies in motion, some, like the sun and stars, exhibit a constant movement, regular in amount and direction, for which no external cause appears. Others, as stones and smoke, seem also to move of themselves when external impediments are taken away. But these appear to tend to move in opposite directions. The bodies we call heavy, such as stones, downwards, and the bodies we call light, at least such as smoke and steam, upwards. And as we further notice that the earth below our feet is made up of heavy matter, while the air above our heads is extremely light matter, it is easy to regard this fact as evidence that the lower region is the place to which heavy things tend, their proper place, in short, while the upper region is the proper place of light things, and to generalize the facts observed by saying that bodies which are free to move tend towards their proper places. All these seem to be natural motions dependent on the inherent faculties or tendencies of bodies themselves. But there are other motions which are artificial or violent, as when a stone is thrown from the hand or is knocked by another stone in motion. In such cases as these, for example, when a stone is cast from the hand, the distance travelled by the stone appears to depend partly on its weight and partly upon the exertion of the thrower, so that, the weight of the stone remaining the same, it looks as if the motive power communicated to it were measured by the distance to which the stone travels, as if, in other words, the power needed to send it 100 yards was twice as great as that needed to send it 50 yards. These apparently obvious conclusions from the everyday appearances of rest and motion fairly represent the state of opinion upon the subject which prevailed among the ancient Greeks, and remained dominant until the age of Galileo. The publication of the Principia of Newton in 1686 and 7 marks the epoch at which the progress of mechanical physics had effected a complete revolution of thought on these subjects. By this time it had been made clear that the old generalizations were either incomplete or totally erroneous, that a body, once set in motion, will continue to move in a straight line for any conceivable time or distance, unless it is interfered with, that any change of motion is proportional to the force which causes it, and takes place in the direction in which that force is exerted, and that, when a body in motion acts as a cause of motion on another, the latter gains as much as the former loses, and vice versa. It is to be noted, however, that while in contradistinction to the ancient idea of the inherent tendency to motion of bodies, the absence of any such spontaneous power of motion was accepted as a physical axiom by the moderns, the old conception virtually maintained itself in a new shape. For in spite of Newton's well-known warning against the absurdity of supposing that one body can act on another at a distance through a vacuum, the ultimate particles of matter were generally assumed to be the seats of perennial causes of motion termed attractive and repulsive forces, in virtue of which any two such particles, without any external impression of motion or intermediate material agent, were supposed to tend to approach or remove from one another, and this view of the duality of the causes of motion is very widely held at the present day. Another important result of investigation attained in the 17th century was the proof and quantitative estimation of physical inertia. In the old philosophy, a curious conjunction of ethical and physical prejudices had led to the notion that there was something ethically bad and physically obstructive about matter. Aristotle attributes all irregularities and apparent dysteleologies in nature to the disobedience or sluggish yielding of matter to the shaping and guiding influence of those reasons and causes which were hypostasized in his ideal forms. In modern science, the conception of inertia, or the resistance to change, of matter is complex. In part, it contains a corollary from the law of causation. A body cannot change its state in respect of rest or motion without a sufficient cause. But in part, it contains generalizations from experience. One of these is that there is no such sufficient cause resident in any body, and that therefore it will rest, or continue in motion, so long as no external cause of change acts upon it. The other is that the effect which the impact of a body in motion produces upon the body on which it impinges depends, other things being alike, on the relation of a certain quality of each which is called mass. Given a cause of motion of a certain value, the amount of motion, measured by distance travelled in a certain time, which it will produce in a given quantity of matter, say a cubic inch, is not always the same, but depends on what that matter is. A cubic inch of iron will go faster than a cubic inch of gold. Hence it appears that since equal amounts of motion have ex hypothesi been produced, the amount of motion in a body does not depend on its speed alone, but on some property of the body. To this the name of mass has been given, and since it seems reasonable to suppose that a large quantity of matter, moving slowly, possesses as much motion as a small quantity moving faster, mass has been held to express quantity of matter. It is further demonstrable that at any given time and place, the relative mass of any two bodies is expressed by the ratio of their weights. When all of these great truths respecting molar motion, or the movements of visible and tangible masses, had been shown to hold good not only of terrestrial bodies, but of all those which constitute the visible universe, and the movements of the macrocosm had thus been expressed by a general mechanical theory, there remained a vast number of phenomena, such as those of light, heat, electricity, magnetism, and those of the physical and chemical changes, which do not involve molar motion. Newton's corpuscular theory of light was an attempt to deal with one great series of these phenomena on mechanical principles, and it maintained its ground until, at the beginning of the 19th century, the undulatory theory proved itself to be a much better working hypothesis. Heat, up to that time, and indeed much later, was regarded as an imponderable substance, caloric, as a thing which was absorbed by bodies when they were warmed, and was given out as they cooled, and which, moreover, was capable of entering into a sort of chemical combination with them, and so becoming latent. Rumford and Davy had given a great blow to this view of heat by proving that the quantity of heat which two portions of the same body could be made to give out by rubbing them together was practically illimitable. This result brought philosophers face to face with the contradiction of supposing that a finite body could contain an infinite quantity of another body. But it was not until 1843 that clear and unquestionable experimental proof was given of the fact that there is a definite relation between mechanical work and heat. That so much work always gives rise, under the same conditions, to so much heat, and so much heat to so much mechanical work. Thus originated the mechanical theory of heat, which became the starting point of the modern doctrine of the conservation of energy. Molar motion had appeared to be destroyed by friction. It was proved that no destruction took place, but that an exact equivalent of the energy of the lost molar motion appears as that of the molecular motion, or motion of the smallest particles of a body, which constitutes heat. The loss of the masses is the gain of their particles. Before 1843, however, the doctrine of conservation of energy had been approached. Bacon's chief contribution to positive science is the happy guess, for the context shows that it was little more, that heat may be a mode of motion. Descartes affirmed the quantity of motion in the world to be constant. Newton nearly gave expression to the complete theorem, while Rumford's and Davy's experiments suggested, though they did not prove, the equivalency of mechanical and thermal energy. Again, the discovery of voltaic electricity and the marvellous development of knowledge in that field, effected by such men as Davy, Faraday, Oersted, Ampere, and Melloni, had brought to light a number of facts which tended to show that the so-called forces at work in light, heat, electricity, and magnetism, in chemical and in mechanical operations, were intimately and, in various cases, quantitatively related. It was demonstrated that any one could be obtained at the expense of any other. An apparatus was devised which exhibited the evolution of all these kinds of action from one source of energy. Hence, the idea of the correlation of forces, which was the immediate forerunner of the doctrine of the conservation of energy. It is a remarkable evidence of the greatness of the progress in this direction which has been effected in our time, that even the second edition of the History of the Inductive Sciences, which was published in 1846, contains no allusion either to the general view of the correlation of forces published in England in 1842, or to the publication in 1843 of the first of the series of experiments by which the mechanical equivalent of heat was correctly ascertained. This is the more curious as Ampere's hypothesis that vibrations of molecules causing and caused by vibrations of the ether constitute heat is discussed. Whewell remarks, apropos of Bacon's definition of heat, that it is an expansive, restrained motion, modified in certain ways, and exerted in the smaller particles of the body. That, although the exact nature of heat is still an obscure and controverted matter, the science of heat now consists of many important truths, and that to none of these truths is there any approximation in Bacon's essay. In point of fact, Bacon's statement, however much open to criticism, does contain a distinct approximation to the most important of all the truths respecting heat which had been discovered when Whewell wrote. Such a failure on the part of a contemporary of great acquirements and remarkable intellectual powers to read the signs of the times is a lesson and a warning worthy of being deeply pondered by anyone who attempts to prognosticate the course of scientific progress. End of Section 2. This is a Librivox recording. All Librivox recordings are in the public domain.